Good afternoon, everybody. I'm Shobha Vasudevan from the University of Illinois at Urbana-Champaign. I'm going to present my paper, Automatic Generation of Assertions from System Level Designs Using Data Mining. This work was done in collaboration with my students, Lingi Liu, David Sheridan, and Viraj Athavale. Lingi Liu is the PhD student who has done a bulk of the work. So let's look at what is assertion generation and what it entails. Assertion generation, whichever level of the system design cycle that it's done, is a very manual process that takes multiple man-months, and it's almost always stipulated as necessary for assertion-based verification or for the verification process in the system level or the register transfer level. So in prior work, we invented a software called Goldmine, which does automatic assertion generation in RTL at the register transfer level of hardware designs. And this Goldmine uses data mining of RTL simulations, and that is the RTL simulations are used as data, and correlations are found by data mining in the RTL simulations, from the RTL simulations. And these correlations are validated using a formal verification engine. So the work that I'm presenting to you today is based off Goldmine, in that it uses the idea of data mining plus static analysis in order to generate assertions automatically. So why do we need assertions at the system level at all? So among the multiple reasons, the top few are as follows. So mining at implementation level or design level yields logic level properties, right? The connection between, relationship between different signals in different cycles, say. But mining at the system level yields higher level or more design intent kind of properties, okay, which are valuable because irrespective of implementation, sometimes you want to check that the specification is being met. So the other reason is that system level assertions can potentially be refined and then mapped onto the RTL and be used in RTL monitoring. The system level assertions could also be used to lace the borders of the RTL blocks, and hence they could be used as a mechanism for lightweight equivalence checking between the system level design, system level model, and the register transfer level design. Another reason is that our previous work did assertion mining from RTL, and the limitation there was that we were generating assertions in RTL, and we were generating it from the RTL itself, so a bug in the RTL could get replicated in the assertions. And so a logical next step in our research was to push this analysis upwards or upstream in the whole design cycle, and that's the reason why we would like to mine assertions at the system level as well. So in order to apply assertion mining at the system level, we need to address these two flavors of system level models. So there are cycle accurate models which have explicit clock signals for synchronization between different events at the system level, and there are transaction level models which do not use such a fine-grained cycle level synchronization, but instead the communication primitive there is much more abstract, and it is a transaction. So assertions that are generated for cycle accurate models should ideally express the logical relationship between the signals in different cycles, so sort of closer to the RT level or the implementation of the system level model. But at transaction level model, at transaction level, you would want the assertions to express more clock cycle agnostic events, which are transactional, or data flow between different blocks, and so on and so forth. So in order to address these two flavors of system level models, we use two different types of mining algorithms: coverage guided association mining, or simply association mining, and sequential pattern mining. Okay, so let's look at a flow of how this assertion generation is done for both these flavors of system design models. So, for the cycle accurate model, the flow is very similar to the gold mine approach for RTL designs. Here the data generator is basically a simulator where the system level design is simulated, and different traces are now the traces form the data for the data mining algorithm, which, as I mentioned, is association mining. There is also some static analysis where a logic cone is inferred for the target output for which we want to generate assertions, so that the mining of associations is kept regulated to the logic cone itself. At the end of this process, candidate assertions or likely assertions are generated, and unlike RTL, where there was a formal verification step to validate this, in this work there is no formal verification step to validate the cycle accurate or the transaction level assertions, because we do not have because we have not yet managed to have access to a system level formal analysis engine that can scale well. So, at the transaction level, again the same the flow is slightly altered, because we use the sequential pattern mining algorithm for the for generating transaction level assertions, and we also use data symbolization, which is basically a technique to generalize or to create a symbolic version of these assertions that are generated by the sequential pattern mining algorithm. Now, in both cases we generate likely assertions or candidate assertions, and these candidate assertions, as I mentioned, can potentially be used can potentially be validated using a formal verifier like BLAST. Another use case for these assertions is to also refine them and further use them in RTL verification. Any kind of evaluation for these assertions through the designers or verification engineers can then go back into the data mining component of the flow in order to provide feedback and generate better assertions. But in this work, we are not going to talk about the validation of these assertions either by formal techniques or by downstream RTL validation. We are going to restrict ourselves to what is outlined by the dotted line here, and this is what this talk is going to be about. So, let us look at association mining for cycle accurate designs. Now, as I mentioned, the association mining is somewhat similar to the approach that was used in the original gold mine tool for RT level assertion mining. There we used a decision tree based supervised learning algorithm. Here the association mining algorithm, although it is similar in spirit to that algorithm, it performs a lot better. So, what that means is the association mining also generates bit level assertions, and it generates assertions on it looks at data on a cycle by cycle basis. It looks at the simulation traces on a cycle by cycle basis. So, the assertions generated are also related. They also relate the signals in multiple cycles to each other. However, we are going to show that the association mining is actually better than the decision tree based original gold mine algorithm, because it manages to provide more succinct and higher coverage assertions. So, in this approach, input space coverage is used to guide the mining process. So, just for simplicity, we have shown a combinational block here with a simulation trace of a combinational block of signals ABC, and the output for which we generate assertions is Z. Now, so this algorithm, the association mining algorithm, has goes through multiple iterations. In every iteration, there is a coverage gain threshold or a minimum coverage gain. Now, what this means is, if there is at the end of every iteration, there is a solution set of assertions that are generated by this algorithm. Now, when it picks an assertion for this solution set, let us say in this case assertion A1 says that if A is equal to 0, then Z should be equal to 0, right. So, if you see this in these simulation traces, that corresponds to 2 entries out of 4 in the simulation trace. So, when you say A1 is this assertion, this means that 2 out of 4 or 50% of coverage has been achieved by this assertion, right. So, now if the association miner tries to pick the next association, which is, let us say, the fact that when B is equal to 0, Z is equal to 0 in the simulation trace, then that corresponds to these two entries. Okay, so this antecedent here corresponds to entry in the row 1 and row 3 of the simulation trace. But between those two entries, row 1 has already been covered by A1. So, the only real value that is being provided by A2 is is a coverage gain of 1 out of 4 entries, or 25%, right. So, if my coverage gain threshold was 50%, then B is equal to 0 implies Z is equal to 0, or the assertion A2 falls below 50%, and so also for assertion A3. So, in the next iteration, if I now decrease the coverage gain or the minimum coverage threshold to 25%, then I can include this assertion A2 in my solution set, but now the other assertions get A3 and A5 get excluded. A4 still stays because it manages to include more than 25%. It manages to the coverage gain because of inclusion of A4 is higher or equal to 25%. So, if you keep going like this, then, and if you go don't go below a minimum coverage gain threshold, then the output assertion set is, in this case, A1, A2 and A4. Okay. So, now we come to the next part of the talk, which is mining information in transaction level designs. So, now that the coverage guided association mining approach has been talked about for cycle accurate